Here is an introduction to the Big Bang to accompany Chapter 29 of the textbook Astronomy from Open Stax. So, the Big Bang, what is it? At the very beginning of the universe, everything was an infinitesimal point. And when I say the universe, and when pretty much anyone says that, what they mean is the observable universe. So everything that we can see within the photon travel time. Um, Is that the whole universe? I don't really know what that means. Maybe not, right? But suddenly, this thing rapidly expanded, right? So, boom, expanded rapidly. Don't think of it as an explosion. Think of it as space itself expanding, and that is the Big Bang. And when we talk about, what is the Big Bang in terms of time, a ballpark, it's the first 3 minutes of the universe. It's the first 3 minutes after this rapid expansion. Um, and that name is particularly popular. 3 minutes isn't exactly accurate, but it's the title of a very nice book by Steven Weinberg. And if any of this interests you at all, it's a nice popular science book written quite a while ago, but very interesting description of the Big Bang at a not too technical level. So, we're talking about the first 3 minutes, and this is when the universe formed the very first chemical elements. So if we look at the periodic table here, then we see most of the elements were made by stars' stellar explosions, but a few were made during the Big Bang. So your hydrogen, your helium, lithium, it's not shown here, but you have a little bit of these other lighter elements can be made in the Big Bang. And 3 minutes might not sound like very much time, considering the universe is about 14 billion years old, but a whole lot happened then. So the universe started out at essentially infinite temperature and density. Um, we say essentially infinite temperature and density because basically our theories that we have run out at a certain point. At an extremely crazy high temperature and crazy high density, basically we can't describe um, anything anymore because we get to a point where things just kind of break down. Essentially what happens is that you have scales that are so small you need quantum mechanics, but gravitational forces that are so high you need gravity. There's no theory of quantum gravity, so we just can't deal with that. So in any case, you go from extremely hot, extremely dense, where that can be an arbitrarily large number for you, and then in the first 3 minutes, you decompress and you get to a much cooler temperature, right? So you're only 1 billion degrees. That's hot, but that's not so bad. And relatively sparse, not too dense. So about as dense as Earth's atmosphere. Um, so that all happens in this first 3 minutes. You form the elements, and you have this just rapid expansion and cooling that occurs due to the expansion. So briefly, at the very beginning of the universe, radiation dominated the universe. And by radiation, I mean photons. So you're probably familiar with the equation E equals mc squared, or at least, we've all heard it. And this is the matter-energy equivalence principle. And so it just means that, you can convert mass into energy and back and forth. And the proportionality between these two things is the speed of light squared. So energy can go into mass and mass into energy. So then if you have extremely high temperatures, this conversion happens very easily, right? So photons can combine to, if they collide with enough energy, to create matter. So for instance, an electron and a positron can be created. And the opposite can happen too. You can have a piece of matter, like an electron, and the antimatter, that's a positron, which is just a positive electron. These can combine and they can form gamma rays. And at high temperatures, this is really happening all the time. You're creating matter and destroying it at a very rapid pace. This happens for brief amounts of time in other astrophysical environments, but the Big Bang is one case where it happens. So at this very early part of the universe, you are radiation dominated. And if this all sounds like hocus pocus, like taking photons and turning it into matter, we do this in the laboratory, actually, sometimes. It's not commonly done, but it is done. So for instance, at the Large Hadron Collider, um, that's a device on the French-Swiss border. It's a very large piece of equipment used for particle physics measurements. Typically, what you're doing is you're colliding particles to make other particles. But some of the time, what you can have happen is your particles can collide like two protons. Um, these can release photons in that collision effectively, and those photons can combine to make other particles. This funny diagram here is known as a Feynman diagram. You don't need to know how it works or what it means. But the point is that this happens in the laboratory. You can take photons, turn it into matter. We, of course, then take matter and antimatter and turn it into photons frequently. That happens all the time. So in the early universe, this was the main thing going on. And since most of the energy in the universe was in the form of photons, and this really drives the physics, we call that the radiation-dominated era. So the early universe was the radiation-dominated era. Now, a few minutes later, when you're much cooler, you're only at 1 billion degrees, that's when you can form atomic nuclei. So the protons and neutrons that are formed at the very early part of the universe, um, these can combine to form atomic nuclei. So for instance, a proton and a neutron can combine to form something called deuterium, which is also known as heavy hydrogen. And then deuterium can burn to create helium. And so this is the main type of helium that we all deal with. You can remove one neutron and you make this thing called helium-3 that is present in very small abundances here on Earth. So at 4 minutes, it was too cool for nucleosynthesis to occur. So that means nuclear reactions creating elements. So you have about a minute, from about 3 minutes to 4 minutes, that the early light elements in the universe were made. So further reactions later on in time in the universe have changed this hydrogen and helium into other stuff. But for the most part, it's changed very little, right? So at the Big Bang, you had essentially 100% hydrogen and helium, or almost that. And now we have 99.8% of our solar system is hydrogen and helium. So the Big Bang pretty much made everything, and to be honest, very little has changed since then. Now, that 0.2% is still very interesting. That's a large part of my career, is looking at the details of that 0.2% of change. But if we're honest with ourselves, for the most part, not a whole lot has changed. And why do we care so much about Big Bang nucleosynthesis, this element formation in the early universe? Besides the fact it's where elements were made, which is kind of cool, that's the big question. We can learn about the Big Bang itself by observing the elements of these. By observing the abundance of these elements for very distant objects. So that gives us the signature of the Big Bang. So why is that? This diagram here on the right, that looks a little bit confusing. What you have is each circle here, this is an isotope of an element. So the element is the horizontal direction that tells you how many protons are in your nucleus. And you can have a different number of neutrons, these neutral particles, and that just changes the isotope of the element. And these are details that you don't need to know the details, but I'm just trying to explain what's going on here in Big Bang nucleosynthesis. So the arrows that connect the different isotopes, these are nuclear reactions. Each of these arrows has a given reaction rate to convert one type of isotope into another, or if you want to think about it that way, one element into another. These arrows have a strong temperature sensitivity and density sensitivity, and so by observing the abundances of these elements, the relative abundances, we can learn how the temperature and density evolved at very early times in the universe and how the Big Bang took place. How we actually observe these so-called primordial abundances, the abundances in the early universe, is pretty tricky, but one way that's kind of fun is you can, for instance, use absorption spectra from quasars. So a quasar is a very bright object at the center of a galaxy with a supermassive black hole, and that winds up generating a lot of light by the supermassive black hole kind of feasting on the surrounding matter. That is basically a really, really bright light bulb that is then behind gas in the universe. And so that light bulb shines on the gas. Some of that light is absorbed. And as we learned in the Introduction to Spectra lecture, you can use that absorption spectrum to tell you what elements you have and how much you have. And so those observations tell you the relative abundances of these elements, and we can use that to learn about the early universe. So a little bit later, only a short 300,000 years, finally it's cool enough where atoms can form. And so what I mean by that is when it's much hotter, the photons that are bouncing around in the universe, these ionize atoms readily, and you can't really have an electron be coherently bound to the atomic nucleus. At 300,000 years roughly, it's finally cool enough, a cool 3,000 Kelvin, which is a bit hotter than a light bulb, and atoms can finally form. So that's kind of cool, but what's maybe a little bit more important, other than the fact that when you have atoms you can now have chemistry, is that because the electrons are now coupled to the atoms, or to the atomic nucleus rather, they're no longer freely scattering photons. So the photons and the electrons decouple. And that means now that photons that are generated around that time can just freely stream outward. They're no longer scattering. So they'll just travel onward until they hit something else. And many of these won't hit anything else. They'll just keep traveling until they reach a telescope here on Earth. And so we can observe photons from this period of decoupling that's about 300,000 years after the very beginning of the universe. We can't technically directly observe anything before that because of these electrons and photons scattering. So that radiation that we receive on Earth, that's known as the cosmic microwave background. And here you are looking at a map of that cosmic microwave background, or that CMB, and the different colors here, these indicate different temperatures. So you can collect the light from different regions of space here, create a black body spectrum like we learned in the Introduction to Light lecture, and you can figure out what the temperature was at that region in space. And this is, you're essentially looking at the whole universe here. You can think of it kind of like a Mercator projection of looking at the Earth. So this is really everything looking out in every direction. So while the universe was quite hot then, 3,000 Kelvin, that light has been traveling a long way, and the universe has steadily been expanding, as we learned in the Introduction to Cosmology lecture. And because the universe is expanding, the photons from then are redshifted, as we discussed in the Introduction to Redshift lecture. And so at this point, that 3,000 Kelvin environment, those photons have been cooled such that it looks like a 3 Kelvin environment. And that is the ambient temperature of the universe. If you go out beyond the solar system, beyond the galaxy cluster that we're in, that sort of vacuum of space is around 3 Kelvin. And so if we want to be able to observe that light, you can recall from the Introduction to Light lecture, we can calculate the wavelength of the photons created in an environment of a given temperature, and we find that that's about 1 millimeter. This is the border of kind of the microwave and radio wave regime, and so that's why we call these photons that we observe the cosmic microwave background. So it's in the microwave wavelength, it's a background because it's literally everywhere you look, and cosmic because it's made, in the universe. So this CMB, this cosmic microwave background, okay, why am I talking about it? What does it tell us about the Big Bang? It tells us a couple of interesting things. So one, we know that the early universe must have been extremely uniform. So I mentioned that these different colors here, these are different temperatures, so it tells you the temperature anisotropy. So the red is relatively hotter, the blue is relatively cooler, but these are tiny, tiny changes. So we're talking about the brightest red that you see here is 0.01% hotter than the average temperature. The darkest blue is around 0.01% cooler. than the average temperature. So just this is really a remarkably uniform environment. That's what you would expect from a very rapid expansion, right? That's not too surprising. But what's important is it's not too uniform, right? So it's not a perfectly smooth environment. You do have local temperature variations. These wind up seeding local density perturbations, which then can form, discrete structures in the universe, like galaxies and galaxy clusters. And so that kind of, at least on a qualitative level, makes sense. On a quantitative level, connecting these temperature anisotropies we see in the cosmic microwave background and our galactic structure is quite complicated. And to even get an introductory grasp, you need to go through the full undergraduate astrophysics sequence, and that's the introductory grasp. So it is a bit complicated, just to be honest. Roughly how this is done is there's a thing called the power spectrum that we can observe here. This basically, what this plot tells you is what is the spatial distribution of these points that are a bit hotter, a bit cooler. So if you were to try to kind of map the distance between the hot points and the distance between the cool points, roughly speaking, you'd get this thing called the power spectrum, and we can relate that to our galactic structure, and it maps up, amazingly well. Now, I don't want to pretend that it's all solved, so the early universe actually leaves a good number of mysteries for us. So one that's kind of interesting is called the cosmic lithium problem. So why is there so little lithium that we observe? So we can predict the amount of lithium that we should have. That's the blue line on these plots tells you the abundance of a given isotope. You don't need to know the details, just the qualitative picture here. So the blue lines, these are predictions. Where they intersect with this kind of ugly, I guess, brownish yellow color, that is what we expect then, right? That is the expected abundance of this isotope, type of element, form of an element in the early universe. The horizontal line, this is the observed primordial abundance of that isotope. So the helium pretty much lines up. So these match quite well. Deuterium matches quite well. When we look at lithium, we predict there's a lot more lithium than we actually observe. And we don't know what the reason for this discrepancy is. We know it's not the nuclear physics that was recently ruled out within the past couple of years through nuclear physics experiments. We don't know what else it could be. Perhaps there's some systematic error in our observations that we just don't understand, don't know is there. Perhaps there's some other mixing process that's depleting this lithium, who knows. Or it could be that, for instance, dark matter is causing reactions in the early universe that we didn't know were there. So that's an outstanding mystery. It's a really big question. A huge question, arguably one of the most important outstanding in physics, is why is there more matter than antimatter? So when we look at this makeup of the universe, most of it's dark energy, most of the rest is dark matter. But when we look at the visible matter, it's pretty much all regular matter. So like an electron, for instance. But the regular matter has an antimatter cousin. So for instance, instead of an electron, you can have a positron. And we can produce this antimatter in the laboratory. But when we look out in the universe, we don't see really any antimatter hanging out. So why is there more matter than antimatter? We don't have a good answer for that at all, which is pretty cool. And another outstanding question in the early universe is, what is the value of the Hubble constant? So in the Introduction to Cosmology lecture, I confidently gave you a value of the Hubble constant, but that is up for some debate. So there are different ways to measure that. I mentioned in that Introduction to Cosmology lecture, you can look at the velocities of objects, velocity versus distance, and that's the black points, and you can get some value. You can extract a different value from the cosmic microwave background, and these don't quite agree. They're not too many error bars away, these vertical lines away, so there's not a super strong tension, but there is some tension. And that is another very interesting, outstanding question when it comes to looking at the Big Bang and the early universe. And that is it for this introduction to the Big Bang for Astronomy 1000.